now we see a talk by my coworker Lars, how to test property or properly. Yes. And the conference where it was originally given was Scala Missouri, as far as I know. Yes. Okay, so please welcome Lars.
Yes, in fact, this project is still very much Japan themed because I gave that talk in Tokyo. I did switch out the venue here. Also, I removed the Japanese subtitles because this talk, when I gave it, had Japanese subtitles for non-English speakers, and I can compile them back in if you want them. So also all of the examples and the pictures and slides will be very much Japan themed. Right. So what I'm going to talk about is basically property testing, and if you paid close attention in the previous talk, then Daniel has already mentioned what that is about. Essentially, it is a different way of testing your code where you don't specify your own test cases, but the framework some framework generates them for you. And yeah, this is the basic idea. Instead of basically calling a function with concrete arguments, you just have a function that takes some parameters, and then the framework will instantiate those parameters. And as I said, I gave the talk in Japan, so I gave the example. It is a bit like going to a restaurant and ordering omakase. I'm not sure who knows that in Japanese culture. It's like ordering the chef's menu. You go to a restaurant and say, like, please give me today's menu, like today's soup and whatever. And the only thing that you expect food. And then the chef will basically do that for you. And if you're lucky, it will not only satisfy the interface food, but also this interface tasty. But in principle, if you go to a restaurant, you only expect food. And then if you order omakase, then this chef will prepare something to their liking for you. Okay, so what does it look like in practice? Let's say we want to implement some multiplication in integers. Let's say this is a domain-specific integer type. Let's say this is not the built-in integer because we already have a multiplication operator. Let's assume that it is some kind of fancy, whatever, money integer or something, some domain-specific code that you wrote, and you want to test that the multiplication behaves as expected. For example, you would expect that the multiplication operator is associative, which is algebra talk for you can swap the parentheses around. So it should be the same thing when you multiply x times y first, and then after that you multiply z. Or if you first multiply y and z, and then you multiply x to that. So that's basically a pretty standard expectation you would have for a multiplication operation, and obviously you don't want to list all the input values for that. Because you have 3 parameters here, and you would need to give a big table of examples, and you don't want to do that. So you use prop.forAll, which is a method that comes from the Scala check library. And then what it basically does, it will look at the types of the parameters and then come up with some input values. And in that case, obviously this will pass because multiplication, let's say you implement it correctly, then it will satisfy that property. And here it tells you it passed 100 tests. And note that it will not tell you which tests. It's just like, it just came up with some tests and all of them were good, so that's fine. ScalaCheck has some ways of telling you what the inputs are generated, so you can do something that's called classification. For example, you can ask, give me the percentage of all the numbers that were even, or something like that. You can do that, but in this talk I'm not going to talk about this because this is a kind of very advanced feature. All right. So what happens if instead of having integers, you use floating point numbers here? Let's assume now these are the actual floating point numbers that you know from Scala or from JVM, and you expect, well, this is multiplication, so it really should be the same thing, right? So it should really be also associative. Unfortunately, as it happens, computers, because this does not hold. Processors do not have an associative multiplication operation for floating point numbers. And here you see, well, it tried to test it. It found 2 input sets that were successful, and then actually could falsify it, which means it found some input values that made the property wrong. And here you can see the inputs now. You have 0, 1, and 2, and here you see, well, you have some very small floating point numbers, and you see here it's 10 to the minus 5, 10 to the minus 4, and here it's 10 to the minus 20. So the third number you have here is a lot smaller than the first 2 numbers you have. And does anybody know why this happens? Anyone have a good idea of floating point numbers? Well, I mean, floating point numbers are terrible, that's the reason, but the specific reason is that floating point numbers they can't store arbitrary amounts of information. So sometimes when you do an operation, you have to kill some bits essentially of precision. And this is exactly what happens here. I'm pretty sure you can read that in somewhere on Wikipedia where it would explain this example in a bit more detail. But anyway, the precise details why it's probably failed are not important. It's just important that ScalaCheck found these examples. It found these numbers that will make it fail, and it will print it for you. So that's pretty cool, I think. Right. So far, I've shown you some ScalaCheck examples. What I'm telling you about is that most of these libraries, there's not just ScalaCheck, there's a bunch of others, they all have some common set of features. Obviously, they differ in details, but I just like to point out some of the commonalities that you would see in arbitrary language. So, for example, if your day-to-day language is Java, then you will find such a library in Java that also has these things. So, for example, most of these, or all of them, they have automatic and custom generators. So automatic generators is like here, where you just specify I want a float, and it will give you a float, and you don't care about what float it is. But you might also want to have custom generator. So for example, when you walk into that Japanese restaurant, you don't just say I want some food. You can, for example, say I want sushi. Right? Or you could narrow that down to some extent. And that sort of goes hand in hand with filtering of inputs. So you can either request an automatic generator and then filter the input, or you can just write your own custom generator for the kind of data that you're after. The third thing is really nice, shrinking of counterexamples, which means that let's say you have a property that takes a list of integers as an input, some kind of function that takes a list of integers as an input, and then it finds a counterexample with 30 integers in that list. Right? You have a list of 30 elements, and it prints that for you. And that would be really bad because now you have to start a debugger and figure out what stuff is going wrong, and if it's an iteration over this list, it's going to take a long time to step through all of this. It would be much nicer if the framework would try to give you a minimal counterexample, like the smallest counterexample that could possibly be there. And many of these tools do that. So they will, if they find a counterexample, they will try to shrink it in some way. Yeah, the classification of inputs I've already mentioned. You can ask the framework, for example, to say, give me the percentage of whatever positive numbers that you generate. This is pretty nice if you have custom generators and you're not sure if your generator logic is correct. So this is basically a way of testing your custom generators. And then the last thing is input and property labeling. So if you have some complicated property that have a lot of conjunctions, have A and B and C and D, you can label all of these parts, and then the framework will tell you which part precisely fails. Now, if you use ScalaCheck, for example, together with ScalaTest or with expectT, then you don't need that because these frameworks have their own notion of ascribing meaning to test failures, where you can get very specific test values. So, but if you use ScalaCheck just by itself, this is very nice to get a closer idea of where stuff went wrong. And this is a short and non-exhaustive list of the entire ecosystem around this concept. And as you can see, there's a bunch of these things. And I think for Scala, since I wrote those slides, another one for Scala popped up. In Java, there's not just Java, there's 5 others also. So you can see, no matter which language you pick, you're probably going to find one, maybe except for COBOL. I'm not sure if there's a property library for COBOL, but I wouldn't rule it out. So anyway, so if you have an existing system and an existing language and want to improve your tests, then it's very likely that you can just do that. In Java, for example, it's pretty nice. There are a bunch of them that integrate with JUnit. So if you have a bunch of JUnit tests, or you can just sneak some property tests in there and nobody will even notice. So you don't have to restructure your entire test suite to accommodate for these libraries. All right, so now that I've shown you the basics, I want to do a deep dive. How do these frameworks actually work? What is this magic that it will give you some input values for free to some extent, or where does it all come from? Okay. So this is the most important slide. If you don't remember anything else from the talk, I want you to remember this slide. How do we come up with values? The basic building blocks that make up ScalaJack are pictured on this slide, and this is also pretty much how all of the other libraries work. You have this generator thing in the center, and the generator of type R, it's an object that knows how to generate R's. So R is some type, could be int, could be float, could be something else, and it knows how to generate them. And how does it generate them? Well, it takes an input from a random number generator. So it takes some kind of randomly generated value, which is just usually an integer. And then it also takes some parameters, for example, a size. So the seed here could be like, I don't know, 42, and the size could be 5, and then the generator knows how to turn that into an integer, something like that. And then the value that gets out of this generator will be put into the prop, which is the property that's being tested. And you can nest it arbitrarily, so if your property requires multiple values, you can just put a bunch of these generators one after the other, and just like generate more and more random values to be fed into that prop. And that's pretty much it. That's the entire idea behind this. And basically, the frameworks differ in a way how this random generation is handled. So some of them are truly random, so if you run the tests twice, you will get completely different test cases. And some others use deterministic randomly, so they will have a fixed seed and then they will generate based on that. And some others do a mixture where they will start with some kind of random value, and then if it fails, they will print the seed. And if you have the seed, you can reproduce the test value. For example, if you run your test on a Jenkins job, for example, and it fails, and you want to reproduce it locally, you can just copy-paste the seed from the test failure, copy-paste it to your own local machine, and then you can run the exact same test cases again. And this is pretty nice. Some other frameworks, they also go so far as they record, so there's basically a side channel here, they record all the failed test cases ever into a file, which you can then commit to your repository. And every time you rerun your test, it will always check the things that have failed before. So let's say your test cases failed at -1 at some point. Then we'll put that -1 into the file, and every time you run a test, it will check -1 again and again and again, because it somehow believes that this is a particularly error-prone input value. And yeah, not all of the frameworks can do that, but many of them can do that. All right. So if you want to generate some values for your complex domain-specific type, you can, for example, say, give me a string, give me an int, give me a long, give me whatever, and then you can create a new instance of your domain type. So far, that's not very exciting. But we also have sometimes a bit more complicated requirements. For example, this. Let's say you want to mock some parts of your code, right? So let's say you are writing a shopping cart. You can put items into the shopping cart, and then it computes the total sum. And for testing the shopping cart, it is pretty much doesn't really matter where the items come from and what their prices are. You just want to make sure that the adding up of the prices works correctly. So you want to abstract away from the fetching the items and fetching the prices from some database, for example. So you might have in your code, you might have a function called getItemByName. And it takes a string and gives you back an integer, which is the price. And it's wrapped in the future because it could be an expensive database access. You might be hitting some kind of SQL database, and that might take a while. So you don't want to run that inside your tests, right? In particular, if you iterate this for 100 times, you're going to make 100 database accesses, which could be, depending on the kind of query, could be very expensive. So you might not want to do that. So the question is, can we generate a random implementation of this? So you have a shopping cart function that depends on another function that gives you prices for items, and you don't care about how that's implemented, you just want to test shopping cart. So why not randomize this function? Why not have an arbitrary implementation here generated by ScalaJack for you that just does whatever instead of hitting the database? Right? Does it make sense so far? So how can we do this? Like, how can we just completely randomly generate this function? Well, there are multiple options here. We could, for example, pre-compute a table. So we could say, well, maybe the compiler somehow comes up with 10 different input values and 10 different output values, and then we just store it into a table, and that's fine. Unfortunately, that's quite impractical, because you can never know how your function is going to be called, what input values it's going to receive. So that's not really practical. Also, it could potentially take a lot of storage in your memory. It could be if you have like a function with 10 different input values, this table could be very large. So that's not a good idea. We could also make our values on the spot. Like whenever we call a function and we're being called with a name or with an input that we haven't seen so far, we could just like create a value at random. And unfortunately, this is side effecting. And as good and pure functional programmers, we don't want to do that. We actually want to do this in a purely functional way without just like poking into mutable state all over the place. We could also just use constant functions. So whatever you give an input, you could always return 0 or 1. And obviously this is not good enough because what good is this? Like this is not really random, right? You're not going to test much. Unfortunately, Scala check before I think 1.12 or something like that, like a few years ago, it did just that. It just only gave you constant functions. And if you're not aware of that, then you would just expect that your tests are truly random when they weren't. Now, luckily, at some point in Scala check, a new feature was implemented that would actually allow you to, like there's a fourth option here essentially, that would satisfy all the constraints. It's random, and it's pure, and it doesn't take a lot of memory. So it's kind of a nice benefit for all of them, taken from all of these options. And the way this works is with a thing that's called cogent. In a few slides before, if you remember, I told you this thing called gen, or generator. Now, cogent is basically a name that's, again, algebra speak, and the co in front of something means sort of like the opposite thing of that thing. So, I don't know, if you're walking up the stairs, then co-walking up the stairs would be walking down. So it's kind of like reversing the thing. It's like the anti-thing, like an anti-gen. It does the opposite thing. I hope that no category theorist is going to watch this because they're literally going to kill me. Because it's not entirely true, it's not entirely accurate, but like for the purpose of this talk, it's good enough. So what's the idea? The function outputs of a function, they must only depend on the inputs. So you don't want any state in there, or you don't want any side effects there. So if I call a function with x twice, it should give the same result. And the problem is that when generating a function, the inputs are not known yet. So there's a trick that you can use. When the function is called, you take the inputs to perturb the random generator. So you have some kind of random generator, your function gets called, and then you somehow modify the random generator to give the thing that you want. What does it look like? This is again a copy from the previous slide. You have the random number generator. It gives a seed into the generator, which then gives a value that you can put into the prop. And now, instead of giving that seed directly into the generator, you first give it into the co-generator, which then sort of changes that seed slightly and then puts it to the generator. And the cool thing is that this part is completely deterministic. So if you call this with the same function arguments twice, it's going to do the same thing. And translated into Scala code, this is what the cogent interface looks like. You just have this single function perturb. It takes a seed, it takes a t, and then it gives you back a new seed. So it sort of modifies the seed. And because this is a little hard to understand from just looking at the slides, I will give a brief demo how that actually works. So I have a Scala shell open here, and basically what I'm going to do now, I'm going to import Scala check. So let me just copy paste this over here. Right, so this is just standard Scala check 1.14, no modifications going on there. And then I can ask for cogent. For example, this would be the cogent instance for string. So I can somehow use strings to modify a random seed. Let's also get a seed. And the seed looks like this. As you can see, the seed is some assortment of integers. Doesn't really matter what it looks like. But anyway, so we have a cogent now. We have a seed, so we can use we can use that cogent to modify the seed. For example, if we call this perturb function here, and we call it for A, then we are going to get a different seed than if we would be calling this for B. So as you can see, the seed changes depending on the input value. And in particular, if you call this perturb twice on the same value, you will get the exact same result. So basically I can ask this, and it's going to be the same thing. So this is completely deterministic. If you call the function twice with the same argument, you're going to get the same output, which satisfies the constraint that we want to be purely functional. You don't want to have any side effects. Right, and you can try this for many other values. So every string that you could possibly give will give you a different seed here. Okay, so in practice, what does it look like? Let's just get the default parameters, and then let's take a generator that only gives us positive numbers. So usually you can ask for a generated integer like this, just call the apply function, and again this is deterministic. If you call it twice with the same inputs, you get the same output. And instead of calling it with the exact seed, I can call it with the perturbed seed. And I'm going to get a different integer out. So, and again I can control this twice, and it's going to be the same result. If I call it with a different input value, it's going to be a different seed. Now the point is, if we look back at this function definition here, a function that takes a string and gives us back an int, this is essentially how it works. You generate a random seed at one point, that's fixed, it's static, and then you take the input string and use that to modify the seed, and then you can put that into the generator for integers. So basically, every time you run the tests, you're going to get a different implementation of the function, a different random implementation, but inside one test case, it's always going to be the same thing. So it cannot possibly be the case that you call this function twice in the same test and get different results. Only if you run the test case again, then you're going to get different results. All right. So, yeah?
So if you would call that code, you will always get a successful future, for example.
Yeah.
But you couldn't have it like, okay, first you get it and then you get a timeout.
Yeah. I mean, you could possibly implement that if you want to account for, I don't know, connection failure or something. But if you're just testing the addition logic of your shopping cart, you probably don't want to take that into account, right? You probably have other tests that test if there's a database access failure or something like that.
But you create the mock yourself.
Sorry?
You create the mock yourself?
Yeah, you could do that.
Like, do you always create it yourself, or is there some way that the framework creates the mock?
Yeah, so literally you can literally ask the framework, give me just an arbitrary function from string to int.
Okay.
So
But you would still have to put that in your mock.
Yeah, so you could say I want arbitrary string to int. I think I forgot to import that. So. Right, so you can literally ask for a random function.
Yeah, but there's just a generator for that.
Yeah,
So,
and that uses the exact mechanism with cogent under the hood. Okay, so let's take a step back for now. I've shown you how you can randomly generate many things with Scala check, basic values like integers, but also functions operating on integers or strings. So why don't we do that all the time for all our tests, right? It seems like a nice idea that you don't have to write down your own test inputs. You can just, let the framework do all of that for you. Obviously, it's not a silver bullet, as no things are in software engineering. There are some pros. For example, it's likely to find input you didn't think about. Scala check, for example, if you ask it to produce a string, it will definitely give you something with Chinese or Japanese characters. And that will break every naive attempt at writing some text processing function, because nobody expects that. So that's pretty nice. And it's very unlikely that, for example, let's say in European countries, that people would think of doing that in their manually written tests, right? People in Japan, software developers in Japan, they would obviously do that. But they might not test with, no, actually I think they will test with Latin characters, but like in Europe, people would not regularly think about using different character sets. And Scala will just use them, and it will break your code, I can guarantee that. Also, it can very easily cover a wide variety of inputs. for example, when you write your test case, you might get exhausted and tired after 5 different test cases, but style check it doesn't get tired. Just like you can ask it for 10,000 different inputs, it'll just do that. It might take a little longer to run, but it's no problem. This can be easily parallelized if you want to. The downside is it's not reproducible. So in the default configuration, every test iteration, so every time you type test into SPT, it might get different results, right? So if you already have non-determinism in your tests because you're testing asynchronous code, you probably won't be very happy about adding more non-deterministic stuff to your tests, right? But this can be to some extent alleviated with these fixed seeds that you will print out, and then you can reproduce that failure locally. Very often you have a high discard ratio, so what does it mean? If you have properties that have some complex invariance, let's say, to go back to the shopping cart example, the values that you get from the database or from your mocked database should always be positive, right? All the prices should be larger than 0. But if you just ask for an int, it could be an arbitrary, it could be a negative int. So what you can do is you can always put additional constraints on your inputs, and depending on how strong those constraints are, ScalaCheck might have to work very hard to come up with a value. For example, if you say, I want integers that are only between 40 and 50, it is going to have to generate a lot of integers until it eventually hits one integer in that range. And all of these frameworks have a property called discard ratio, and it basically can tell you, well, for every single input that is successful, I should have at most 10 that were not successful, and if it exceeds that, it will print a failure. Say, well, I have no idea how to satisfy your inputs. And the reason for this, otherwise your test case might be looping, right? It might, if you ask for an impossible input, like if you ask for an input that's larger than 40, but less than 30, it's not going to be able to come up with a value for you, so it might loop, and in order to not loop, there's this thing called discard ratio. And this is something that you have to keep in mind when writing the properties, because very often when you filter the inputs, you might run into these cases. And also, existential properties are difficult. Now, what does it mean? Existential properties, it's not some philosophical thing about life and existence. It's basically a property that said, well, there is exactly one input value such that something holds. And that can mean, for example, you want to, I don't know, like you have a function that takes 2 arguments, and the second argument must be in some relationship to the first argument, something like that. And this is very hard to test with ScalaCheck. But there are other testing paradigms in this space that would allow you to sort of alleviate some of these downsides while still keeping the upsides. And the thing that I'm going to talk about now, they are not implemented in ScalaCheck, and as far as I know, there's no actively maintained Scala library that implements them. But if you want them, you can just, it's basically like a design pattern. You can put that into your own code. It's not going to be a lot of code to make that happen. So basically the idea is instead of randomly generating inputs, you just generate all the inputs. Not just at random, like 100 at random, you just generate them all. And this is what I mean with enumerating things. So you would have a type T, and you want to get these inputs of type T, and you just like generate a stream of all of them. So you have a function that's called enumerate. It takes a size, so again, like if you want to make all the lists of size 10, and then you would get a stream, which is a lazy list basically, of all the possible inputs, because they could potentially be large, so you don't want to store all of them in memory, you just want to go through them one by one. And yeah, depending on what size you give, it might be a lot of different things, right? If you ask for all lists of strings of size 10, that's going to be a lot of lists and a lot of strings. So most likely in your test, you wouldn't want to put 10 in here. You might want to put 4 or 5 in there, but nothing larger than that, unless you want to be really sure that it works. Yeah, in Haskell, there's a library that implements that. It's called smallcheck, and the name sort of already hints at that. It's not quick as quick check, which does things at random. Instead, it produces stuff that's small, but it produces all of them. And it does support these quantifiers. So this is again some mathematics symbols. You have existence quantifier, which means there is an input value that satisfies something. You have unique existence, which means there's exactly one input that satisfies something. Then you have the universal quantifier, which means for all inputs something else, which is the stuff that Scholarcheck also supports. Also, it can do implications. So you can say if a property P holds, then another property Q holds. And also quantifiers that are nested in this implication. So you can say if for all x some property holds, then there exists a y such that some other property holds. So you can do like arbitrary complex properties that you can write down. And I'm not exactly sure if there are a lot of real-world use cases for this, but I'm sure you can come up with some kind of business invariance on some kind of domain-specific code that requires some kind of very complicated properties. But I don't know. For my part, when I've been using this in Haskell, mostly I've only used these two things, but none of these nesting business there. Right. I have a small demo, and let's hope this works because I used Docker to build this. Not entirely convinced this far. Okay, so a nice use case for this is if you implement a function that checks if a number is prime. Now let's ignore that every standard library has that already, but I just want to show what's going on there. So again, I need to import some stuff. Okay. So now I will define a function that checks if a number is prime, and for now I'm just going to put a fake implementation here that always says true. Right. So this function will always say prime 4 is prime and 5 is prime and everything else is also prime. So obviously this is wrong. So we now want to write some tests that will catch that error. And basically what smallcheck allows us to do, smallcheck allows us to write down the exact mathematical specification of what it means for a number to be prime. And yeah, I have to make this a little smaller now, I think. So this is going to be a little bit of a ride. So we're going to define a property that takes a positive number. So it's not really important that you understand the full Haskell syntax. I'm just going to listen to me what I'm talking instead of looking at this. So we define a property that takes a positive number, and then we need to define what it means for a number to be a factor of another number. So this is the part that does that. So we take in the number d, and what is it if d is a factor of n? Well, d must be unequal to 1, it must be unequal to n, and the modulus must be 0. And then d is a factor of n. So we have to find this, and then now what is the property would we check? Well, we want to check that if there is a factor, so if there exists a factor, then n should not be prime. Because that is what it means the number is prime, right? It's prime if there's no factor that's unequal from 1 and n. And then we can call smallcheck, size of 10, and then it will print that and it will say, well, I'm failed test number 4, and it says that there exists 4, yeah, it's a number that exists, such that the condition is false, which means in that case 4 apparently has a factor, and in that case the factor is 2, and that means the test failed. Now we could fix that implementation, but that's besides the point. I just want to point out that if you have some kind of problem domain where you have a very exact mathematical specification of what you want, then these kinds of testing techniques are very nice because you can just exhaustively generate all the values, and that means you also get all the corner cases because you have all the cases, right? Yeah, as I said, unfortunately there seems to be no active Scala implementation, but the code necessary to make something like this happen, I think it would fit on like 2 pages or something. It's not too much of a hassle to implement it yourself if you really need that. All right. Okay, so far what I've shown you are properties that we're always talking about a specific type. So we had strings, we had integers, and also the small check example, it was talking about prime factors of integers. But sometimes you may have code that's actually polymorphic, which means it works on arbitrary types. This would be a property that tests something from the Scala standard library. You have a list of an arbitrary type A, and you want to make sure that if you reverse that list twice, you get the original list back. Of course, it's something that you would expect from a reverse function, right? If you reverse twice, you get the same list back. Unfortunately, there's a catch. Because this property, as it was written, would give you a compile error. There's no way that Scala check can test it because it doesn't know what A is. It doesn't know how to generate A's because it's just some opaque type. You can't look at it. Right? So the question is, how should we instantiate A? What should we use? In particular, there's a nice problem here. If you use a type that only has exactly one value, like unit, this thing may hold in more cases than you would expect. If you have a list of units, then the reverse of a list is exactly the same as the list itself. So even if you have a false reverse impression, you might not catch it. Right? So you can't just use an arbitrary A. You have to think very hard about what A's you should be using. The question, should we come up with fresh types? Should the testing framework just generate new types, like it generates values? Would that even work? Like, couldn't we even do that? Yeah, but essentially the problem here is we've seen how these frameworks come up with values, but can they also come up with types? And the answer is no, they don't. So this is another thing that's not implemented. But if you need it, you can also implement it yourself. It's not going to be not going to take a lot of code. And the thing that I'm going to show you now requires a little bit of knowledge about the Scala type system. Because it is a little bit complicated to actually make that happen. So the idea is basically you define an interface that's just called type. And that interface just contains a type T that we don't know anything about. And this is something that you can do in Scala. You can associate a type to an interface and you leave it completely unspecified. So everyone who inherits from that or from the interface can put an arbitrary type in there. And the catch is that you know nothing about that T. There's no upper bounds, no lower bounds, no anything. But you can generate values of it because you have a generator here. And you know that that generator T is exactly that same T. But you don't know what the T is, right? So I have a demo for this. And I'm not going to show you all of the code that makes it work. I just want to show you that you can do it if you really want to. So let's get rid of that Haskell stuff again. Okay, so I will just restart the Scala repo. Okay, but I need to copy paste a bunch more things now. Oops. I think I forgot the I again from the import. Sorry about that. Okay, let's try this again. Okay, that's correct. I need to copy paste some more things. We didn't see any of that, obviously. It's just like the matrix scrolling past you. Okay, now what we can do is we can define a polymorphic property. And what? Malform. That's interesting. Malform class name. Oh, nice. I have no idea what's wrong here. What? Okay. Just going to put a workaround in here. I swear this didn't happen last time I gave that talk. Okay, let's try this again. Ah, now it works. Okay, fine. So we now have defined a polymorphic property, and what does it do? I think it's a little bit larger again. Well, we say we want to have for all property, and now we are not quantifying our value, we're quantifying our type. So we say, give me any small type t, and then I can call in t.for all. I can say, well, for all x and y, x should be equal to y. And obviously it's going to fail because not all x are equal to all y. And I can use the normal check function from ScalaCheck now, and it's going to give me a counterexample. And this foo is the workaround I put in here. It's supposed to print the name of the type, but apparently that doesn't work anymore. And what it tells you is, well, I have instantiated it with some b and some a. You don't know anything about it, but you know that b is unequal to a. So it basically puts some types that you don't know anything about into your function, and then it will see if that function works correctly. And if it works, then it will just use another type, other values that you know nothing about, and so on and so forth. And what is that good for? Well, it's good for testing data pipelines. So in particular, if you're in the business of streaming data, you are probably going to use some kind of framework like Akka Streams or Spark or Flink or whatever it's called. And these will have some kind of operations that will transform data. So maybe you have a data set, and then you can apply a map operation or a filter operation, all of these things. And let's just assume that you're implementing such a thing. Let's assume you're not using them, you're implementing them. You want to make sure that all of these transformation routines work correctly. And now you're hard-pressed to come up with random functions that have random types. So you want to have a map operation on some data set that maps from an arbitrary t to an arbitrary u, and also does that in an arbitrary way, right? So if you're just using random function generation, you have to be very specific about the types that you put in there, like string to int, into string, something like that. But you can use that stuff for actually generating types, and you can generate random graphs of string transformations with random types. And I find that very, very, very useful. Also, if you're in the business of implementing compilers, then you can use that to generate well-typed trees. There's a talk from Eric Oshheim at FlatMap this year. I will put the slides online. It's actually a link you can click. And we'll give the recording of this year's FlatMap Oslo. And there's specifically a talk from Eric about exactly that use case, how to test data pipelines. Yeah, and I'm sure he did a much better job at explaining this than I did in these 5 minutes. Okay, so what else is there? Outlook. What other things can we do with this? So first of all, the interesting bit is that there's still innovation happening in the space. Even though property testing, the concept itself is quite old and sort of well-known in functional programming, a lot of stuff is still happening. One thing is law management and checking. So if you have some complex invariance on your types or interfaces, you can use libraries to package up some laws that all of these implementations have to adhere to, and then you can just say, well, check all the whatever laws for this type. And those work with regular inheritance and stuff like that. Integrated shrinking means that you don't have to take care of implementing shrinking yourself. The system sort of does that for you. Automatic classification of counterexamples. Now this is very interesting. Let's say you have a function that takes two lists as an input, and it always fails if the two lists have the same length for some reason. But it might be working if you have two lists that have a different length. Now, ScalaCheck would give you one exact counterexample, would for example, like this list has size 1, this other list has size 2, and it fails. But you don't know, sorry, this list has size 1 and this other list has also size 1 and it fails. But you have no idea why it fails for that. So there are some tools that can actually, they will still continue finding more counterexamples after they have found one, and then they will look for patterns in these counterexamples. So they might be able to tell you, well, it always fails, as far as I know, if those two things have the same length, which I found very interesting. Also, automatic generation of properties. So maybe you have no idea what invariance should hold over your code. So there are tools that will just like look at the functional program and then will try to come up with actual properties that are satisfied. So that will be for the very lazy people. Just want to write code but don't want to write tests. So you run this and will even generate the tests for you. And then, of course, the next thing, like the next level thing you could do would be writing proofs instead of tests. Because if you're writing properties, those are things that should probably hold for all the input values. So the first simple thing is you can write simple test case. You could use quick check, you could use small check, or you could use some proof assistant that will actually prove that for you. And for Scala, there's actually a proof assistant that understands Scala code. If you want to know more about this, just talk to me afterwards. And you can write real Scala code, and it will automatically verify these properties for you. There's no testing involved, and you can be 100% sure that it works. All right, that's all I got. If you have any questions, feel free to ask now or over a beer.